Okay. So I guess before you present Celine, I'll just briefly introduce that. Everyone. So Celine is one of the undergrads in my group, and so she's gonna present about her yellow fever virus project and some preliminary results. So yeah. So with that, yeah, you can take it away, Celine. Yeah.
Yeah, just like she mentioned, I'm still like going over a few more things. So it's not completely done. So it'd be nice to hear a bit of your guys' input on it as well. So I'm doing a yellow fever virus, which I was given with Shaw and also Shirley as well. So to go over a bit. So I was given a research document to look over, which is the antiviral research, which it basically presented a NS5 protein and it has a replication of a Faller-Ahn virus, which I would it both have like a variation of N-terminal methyl transfer domain and the C-terminal RNA. So since they're both combined, I have to get that like accounted for. And basically, it had in this research document, it had the yellow fever NS5 enzyme at 3.1 Angstrom resolution. So basically, with that, it would reveal like a right hand fold, a viral like polymers, and it would basically highlight the conservation of the region of the yellow fever virus, which would help structure the aid for like drug design. So I was basically wanted to like look at like that if I could like recreate that. And so the results from that research, it was basically they created a crystal with the 3 Angstrom, which is shown like in the right figure right here. And from those figures, like the first one was mostly when it had like the positive charge of the optimized RNA, and then the second one was about like the yellow fever RNA domain colored of the sequence conserved. And the last one kind of just showed the combination sequence of the structure flarevirus of the NS5. So to find like a similar one that has like the yellow fever structure, I was given the 6SQN, which is a PDB. And that one basically is a crystal structure of the yellow fever virus polymer of NS5A. So what I was trying to do was mostly checking on the ligands. I would have to include both ligands since they are both important. I was trying to do one with just only zinc to see if there was going to be a difference with it, and one I'm currently still working on, which I don't have any results yet at all, which is going to be a zinc combination with SAH, which the SAH is shown in the figure here. I don't know how that result would be, but I know currently when I was working with SAH, the diagram kind of looks off on just SAH by itself. So I'm trying to just make sure if it is going to be correct. But I do have a result for zinc, and I know zinc is basically could help bind the sites to conserve NS5 proteins from the yellow fever virus. So with that, I was able to implement it with the PDB, which when I was trying to find the parameters, I was able to find the volume, which is shown there in Angstroms. And with the parameter, I was able to find the amount of atoms, which I added the 78 atoms for sodium and also the chlorine. And it still had about 36 electrons left over. And I was able to get rid of that by adding 36 more chlorines. And I used like an OPC box of 15. And with that, I was with the heat and minimization, I was able to create this video that's shown here of how it kind of looked, which is kind of similar to like the image the research had from the yellow fever virus. I still have to look more into if it's like anything different from the protein, which I really am not sure yet. But just to compare the two from here, it's kind of just upside down for what I have, but it's somewhat close. I still have to probably still compare more on that. But as like the results from like the minimization and heat, I was able to get the density, temperature, and energies from it. And we could see that for the temperature, it was able to get stabilized around like 300 Kelvin. And for the energies, I know it's kind of hard to see. I wasn't sure on how to change the colors of like the graphs from the energies, but I know it's kind of hard to see. But it kind of starts up here from 0 and just stay constant up here. And there's like mostly some down here, but that's kind of like the energies I was able to find from it. And I don't really have much from it, to be totally honest, but that's basically all I have.
Yeah, I think that's great. Yeah. Oh, we have questions. Yeah.
Thank you.
Why
Yeah.
is density increasing with time?
Why is density going with time?
Yeah, going
The density. Yeah.
I had the same question. Yeah.
Yeah, I was just seeing like how the densities were just affected through time. I haven't like analyzed it too much, and I don't know why it's just going with time. I thought it'd be constant as well. I don't know if I did any errors on probably figuring out from the analysis.
Well,
So-
did you like did you check any literature which perhaps gives the density of the protein that you're looking at? Because even when you go to the previous slide, your I don't know whether how you chose the volume of the unit cell. And just one suggestion: if the number in angstrom cube is too high, is so high as you're showing here, it's better
Yeah.
to put it as nanometer cube rather than angstrom cube.
Yeah, so basically when I use the information, let me see if I can find that real quick. So I basically used the water optic information when I was trying to use the T-leap information. And when I inputted the module of the 6QS in PDB, I mostly only included the zinc variable and I had still like the other atoms of it. And when it calculated the volume for it, it showed the volume to be so high, like it's shown here. I don't know why I clicked that, but in the end, like when I was found the volume, I was able to just find the atoms for it. So that I don't know why again it's like such a high volume.
I think I may have missed what you were saying, but my question was like, how did you define the initial unit cell, the volume of the unit cell? Did you have any literature parameter which gave you the density? Suppose I'm doing a water simulation, I have 100 atoms of water. I know that the density of water at 300 Kelvin is 1000 kg per meter cube. So I basically calculate the initial unit cell volume and then I optimize its geometry and do the energy minimization. So did you have any literature which looked at the density of the crystalline structure of the yellow fever virus?
To look at the exact density,
Yeah, because your density was varying from like 50,000 to 1 e raised to 5, which is a very big jump. So
yeah.
I think it means that your initial unit cell parameters were way off from what it should be actually.
All right.
Yeah.
And did you add water to it?
Yeah,
Okay.
I added water.
Sometimes you might get errors if you don't correct for PVC, the trajectory, because you're calculating density over time. So try to do boundary corrections. And when you output density, do you output density of the protein or density of the system?
I believe it should be the whole system.
Okay, so it's the water plus the yellow fever.
Yeah.
Protein. It's the protein, right? Protein plus the water.
Yeah, but then I also did a trip cage of it just to focus on the protein. I don't think I readjusted that from my density, so I think it's just taking account with the water currently.
Yeah, I would suggest first calculate the density of water and see if it matches. I don't know if you're using 3P or spec one.
OPC.
Oh,
OPC, it's OPC. Yeah.
Yeah, and check for like what is the density for that the force field generally gives for that water system. Yeah. And then calculate maybe for the protein.
Yeah, we could take a look at the density together, Celine, sometime to see why it's increasing, because that does
Yeah.
a bit strange, but maybe it's because you combine like maybe all the steps like minimization, heating, like equilibration, like all of that data. But
Yeah, we
I think it looks
combined all of
good.
that.
I
Mhm.
think one more question is that the I don't know whether I'm going beyond the limits, but when you were doing the energy minimizations, did you see the convergence of the maximum force?
So let me check right now because I have it out actually right now.
Oh, but yeah, Siddharth, going back to your question, so for this one, I think we were only given the ionic concentration, like we weren't given the volume or anything. So that volume that Celine was showing was just automatically calculated from Amber Tea Leaf when we were setting up the system. Yeah,
see.
so yeah, so I don't think there's anything wrong with like the volume size or like the ions added, but yeah, we just have to look at the density. Like everything else seems to be
Yeah.
okay.
I think so. When I first saw the graph, my first intuition was maybe the unit cell was too big initially.
I
Then
think
it is
should be-
reconverging. The
Yeah.
unit cell volume is like going down, which is why the density is going up.
I think the unit cell is fine, but yeah, I mean, maybe it's because we didn't correct for PBC or something.
Yeah.
Yeah, we'll see.
Yeah, there are a lot of interactions could be
Yeah.
because of the image convention.
Yeah.
mhm.
But yeah, I think the minimization, I think Celine has it, but I think from looking at it like a while ago, I think it was fine. I think it converged. We did it in two steps, like where the first step was like we have a restraint on the heavy atoms, so we're just like minimizing the water, and then the second step is just minimizing the whole system. So yeah. So I think it should be
But
okay.
I think sometimes in such MD simulator, like from what I used to observe, like we used to get an energy minimization, but it generally used to take a lot of steps for it to converge to a particular max force. So what we used to do was that we used to do the energy minimizations. We used to do the iterations of those energy minimizations until the max force is like exact to maybe 3 decimals or 4 decimals for the next for 3 consecutive iterations. Then we
Oh,
used to assume that okay, now the energy is now the geometry has been optimized perfectly,
okay.
because there might be some kind of like even in the energy minimizations when we used to look at the literature, there might be some kind of intermediate states which are a little more stable. So we that's why we had to redo our continue our energy minimization iterations so that we actually get to the actual lowest energy geometry.
I see. I think minimization is like really important for DFT calculations, but for
Yeah.
MD, like it just needs to be good enough so that when we're at the heating and equilibrium stage, like it doesn't have any stereo clashes and the simulation doesn't crash, because like we have all these like very extensive stages, so that like once we get to the production, we can gather the statistics, etc. Yeah.
And even in the production run, you generally take after 300 nanoseconds, because by then you're good.
Yeah.
So,
Mhm.
and I think you might have given the convergence value or the force to be less than 1000 kilojoules per mole per nanometer, I guess, in your MDP file, right? Because it's converged.
Yeah.
And that's the typical value we generally do use in MD,
Yeah.
10 per 6, I think it is.
Yeah.
Is it 6?
Yeah, 6.
Yeah.
Yeah.
Yeah, I think it looks good.
Yeah. Do you guys have any more questions?
I think on a more maybe I'm wrong, but is there any particular reason why the crystalline form of the yellow fever is taken? Like, is it only to maintain the periodic boundary conditions, or is there any other reason?
Oh, wait, sorry. Can you say that again? The
No,
question.
this is just more of a doubt for me rather than a question. My doubt was that why did you take a system of like the yellow fever virus? Why did you take a crystalline form, and why not uh, another another type of PDB form? Is it just to maintain the periodicity of
Oh, no, this is the only PDB where they resolve the full structure. This is, yeah, so
Yeah.
there's no choice.
Yeah, there's basically no choice. This is like the only one we
Yeah.
could use.
Yeah.
You can run AlphaFold
Uh,
if you have the sequence and try to match the two and see. Yeah.
that's true, but I don't know.
I mean, it's not required.
Yeah.
Depends.
Yeah. My personal preference is to go with the experimental structure if it's available. So yeah.
So is it like a can you go back to the structure?
Yeah.
So is this like there are domains in this structure, is it? Are there like 3 chains in it? Is it like a trimer or is it a
two chains.
2 chains?
Yeah.
It's very hard to see.
Yeah, it's kind of hard to see. Yeah.
It's really hard to see. I was trying to get a better image of it. It's kind of hard to. For some reason, the BMD was not letting me.
And I think just one suggestion, like the volume is like when you're taking angstrom cube units, it's too high. So I suggest that just make it in terms of nanometer cube, so that you can reduce the number of significant digits, because there is about, about 10 or 11 significant digits total. So it is
Yeah.
yeah.
Okay.
The MD accuracy is not to that level for sure. So
Okay.
You can't simulate this
But-
in DF.
Yeah, but we never report the volume actually for the system. Like we only report the the
Yes.
ionic concentration and all those other things. But yeah, so it's okay. Yeah.
Sorry. My bad.
Yeah.
You just need all these stuff so that the structure is stable.
Yeah.
So to be frank, if you mess up something, the system will crash in the MD run. So you'll know, okay, what's wrong.
Yeah.
And it's only statistical average and then not accurate, but yeah.
Okay, so I think that's good. So let's thank Celine for her presentation. And before we end, I'm gonna stop recording.